Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video, turning IT knowledge into career opportunities. Picture a hospital system that screens thousands of chest X-rays and flags suspicious ones for a radiologist to review. No one sat down and wrote a rule for every possible shadow, fracture, or abnormality. Instead, the system learned patterns from past images. That's where terms like artificial intelligence, machine learning, and deep learning start to connect. And then there's another term you hear everywhere today: generative AI. It overlaps with these technologies, but it describes something different: systems designed to generate new content. By the end of this video, you'll understand exactly how AI, machine learning, deep learning, and generative AI relate, and where large language models fit into the picture. More importantly, you'll know which term to use when someone asks you about them in an interview. Here's what you'll walk away able to do. 1. Explain how artificial intelligence, machine learning, deep learning, and generative AI relate, and where large language models fit. 2. Match real IT problems such as fraud detection, image recognition, log analysis, ticket classification, and code generation to an appropriate AI approach. 3. Explain the difference between prediction, classification, retrieval, and generation. And 4. Correct one of the most common interview mistakes: treating AI, machine learning, deep learning, and generative AI as either completely separate technologies or forcing all four into one oversimplified hierarchy. By the end, you won't just recognize the terms, you'll understand what each one actually tells you about an AI system. Don't picture four competing technologies, but don't force all four into perfect nesting dolls either. Here's the cleaner map. Artificial intelligence, or AI, is the broad field. Inside AI sits machine learning, approaches that learn patterns from data instead of relying only on handwritten rules. Inside machine learning sits deep learning, machine learning approaches built around neural networks with multiple layers of learned representations. Now add generative AI. Generative AI describes AI systems designed to create new content: text, images, audio, video, code, and more. Most of today's powerful generative AI systems are built using deep learning. That includes large language models and modern image generation systems. So remember the relationship like this: AI is the broad field. Machine learning is a major approach within AI. Deep learning is a type of machine learning. Generative AI focuses on creating new content, and modern GenAI is largely powered by deep learning. That map is more useful than trying to force every technology into four perfect circles. An email from your bank hits your inbox at 2 in the morning. It has the right logo, a panicked message, and a link to verify your account. Your spam filter doesn't fall for it, not because a human wrote a rule for every scammer, but because the system learned what phishing looks like from millions of examples. That's why AI exists. Humans can't handwrite rules for every real-world case. At its simplest, artificial intelligence means building systems that do tasks normally requiring human intelligence, reasoning, understanding language, recognizing images. The key correction: AI includes both rule-based systems, like old expert systems, and learning systems, like machine learning. AI is the goal, not one specific method. That single distinction clears up half the interview confusion. Quick recall check. Which statement is correct? Option 1. AI, machine learning, deep learning, and generative AI are 4 completely separate technologies. Option 2. Machine learning is part of AI. Deep learning is part of machine learning, and most modern generative AI systems are built using deep learning. The answer is option 2. AI is the broad field. Machine learning learns patterns from data. Deep learning uses multi-layer neural networks. And generative AI describes systems designed to create new content. So don't memorize AI, then ML, then deep learning, then GenAI as 4 mandatory nesting dolls. Remember the relationships and what each term actually describes. Quick recall check before we move on. Which of these is not required for something to be called AI? Performs a human-like task, must learn from data, or can include rule-based systems. The false one is must learn from data. An expert system that follows fixed rules is still AI. AI is the broad goal, not one technique. A bank's fraud model just flagged a $2 gas purchase as suspicious. That sounds insane until you learn the cardholder's normal pattern. 12 years of filling up at a nearby station. Never $2, never at 4 in the morning. The bank didn't program the rule gas under $3 is fraud. The model inferred it from data. That's the shift machine learning brings. Here's the basic machine learning lifecycle. First, you collect and prepare training data. Then an algorithm learns patterns from that data during training. The result is a trained model. Now new data arrives. Maybe it's a transaction, an email, a support ticket, or a sensor reading. The trained model uses what it learned to make a prediction. That's called inference. Now here's an important correction. The model doesn't necessarily update itself every time it makes a prediction. In many production systems, predictions are collected and evaluated separately. Engineers may later add new labeled data, retrain the model, test the new version, and deploy it. So think: training, model, inference, evaluation, optional retraining. And the core machine learning distinction remains. The behavior was learned from data instead of being completely specified through handwritten rules. A widely used machine learning pattern looks like this. You import a classifier from scikit-learn, create the model, then call fit with your training data and labels. That fit call is where learning happens. No human writes ticket rules. After fitting, you call predict on new examples and get a classification. 4 lines, 0 magic. Machine learning isn't a future project. You already run it every day. A spam filter takes incoming email text and outputs one of 2 labels, spam or not spam. A fraud model takes transaction details and outputs a risk score. A recommendation engine takes click and watch history and outputs the next item to show. Predictive maintenance takes sensor readings and outputs a likely failure window. Same pattern every time. Data in, prediction out. Quick checkpoint. A bank builds a fraud detection system using years of historical transaction data. The system learns patterns associated with legitimate and suspicious transactions. Why is that machine learning rather than simply rule-based AI? Because the behavior was learned from data. But be careful with one common misconception. The deployed model doesn't necessarily get smarter automatically every time another transaction occurs. Many production ML systems separate prediction from training. The model makes predictions. Engineers collect new outcomes. They evaluate performance. And when appropriate, they retrain and deploy an improved model. That's the signature you should remember. Machine learning learns patterns from data. That doesn't mean every machine learning system continuously retrains itself. Your photo app just grouped thousands of pictures of your dog. Think about how difficult that problem is. Different lighting, different angles, different backgrounds. Your dog running, sleeping, half hidden behind the couch. In traditional machine learning workflows, engineers often spend significant effort deciding which features should represent the input. Deep learning changed that process dramatically. Instead of requiring humans to manually define every useful visual feature, deep neural networks can learn increasingly useful representations from the training data itself. Early layers might respond to simple visual patterns. Later layers can represent increasingly complex features. That doesn't mean deep learning requires no engineering. You still need good data, pre-processing, architecture choices, training, evaluation, and production infrastructure. But deep learning can dramatically reduce the amount of manual feature engineering required for complex data such as images, audio, and language. That's one reason it became so powerful. Here's where many AI diagrams create confusion. They try to force everything into 4 perfect circles: AI, machine learning, deep learning, generative AI. The first 3 have a clean hierarchy. Deep learning is a type of machine learning. Machine learning is part of artificial intelligence. Generative AI is better understood by what the system is designed to do: generate new content. Most of the modern GenAI systems you hear about today, including large language models and modern image generators, are powered by deep learning. So, there's a strong relationship. But the most useful question isn't, which perfect circle does this belong inside? It's, what does this term actually tell me about the system? Machine learning tells you something about how the system learns. Deep learning tells you about the underlying neural network approach. Generative AI tells you about the system's ability to generate new content. Keep those distinctions straight, and the terminology becomes much easier. Here's the basic idea behind a deep neural network. Data enters the network. Then information passes through multiple layers of learned representations. For an image task, earlier layers might learn simple visual patterns such as edges or textures. Later layers can represent increasingly complex patterns useful for recognizing objects. That's where the word deep comes from. Deep learning uses neural networks with multiple layers of learned representations. But don't turn deep into a competition where more layers automatically means more intelligence. Architecture matters, training data matters, model size matters, the learning objective matters, and the problem you're solving matters. The important distinction is that deep learning can learn hierarchical representations from complex data instead of requiring engineers to manually specify every useful feature. That's why it became so effective for images, audio, language, and other high-dimensional data. Deep learning has become especially powerful in areas involving complex, high-dimensional, or unstructured data, computer vision, images and video, speech, audio recognition, and speech generation, natural language processing, translation, summarization, question answering, and language understanding, and complex perception systems used in areas such as autonomous vehicles. The common thread is that manually defining every useful feature can become extremely difficult. Deep learning can learn useful representations directly from large amounts of data, but don't interpret that as unstructured data always means deep learning. Traditional machine learning remains extremely useful, and sometimes a simpler model is cheaper, faster, easier to explain, and completely sufficient. The goal isn't to choose the most impressive technology, it's to choose the approach that solves the problem effectively. Here's a better way to compare traditional machine learning and deep learning. Traditional machine learning often works extremely well with structured data, rows, columns, known business variables, engineered features, and relatively manageable datasets. Deep learning becomes especially attractive when the input is complex: images, audio, natural language, video, or other high-dimensional data. Another major difference is feature engineering. Traditional ML often depends more heavily on humans deciding which features should represent the problem. Deep learning can learn many useful representations automatically during training. But there's a trade-off. Deep learning can require substantially more compute, data, training infrastructure, and operational complexity. So don't think deep learning is the upgraded version of machine learning. Think deep learning is one powerful type of machine learning with different strengths, costs, and requirements. Use it when those strengths match the problem. Quick checkpoint. What does the word deep in deep learning actually refer to? It refers to neural networks with multiple layers of learned representations. For an image task, earlier layers might respond to relatively simple patterns such as edges and textures. Later layers can represent increasingly complex patterns useful for recognizing objects. That's part of what makes deep learning so powerful for images, audio, language, and other complex data. But here's the important correction. More layers don't automatically mean a smarter model. Architecture matters. Training data matters. The learning objective matters. Compute matters. And the problem you're trying to solve matters. So don't say, deep learning is smarter because it has more layers. Say, deep learning uses multi-layer neural networks that can learn increasingly complex representations from data. That's the distinction worth remembering. A developer types 10 words. Write a Python script to monitor disk space on 50 servers. 10 seconds later, working code appears. That's not search. Search would have retrieved an existing Stack Overflow thread. This is generation. The system has learned what monitoring scripts look like from millions of examples, and it's producing a brand new one that follows those patterns. That shift, from finding existing content to creating new content, is the entire idea behind generative AI. Now we reach generative AI. Generative AI describes systems designed to produce new content based on patterns learned from data. That content might be text, images, audio, video, code, or other forms of data. Most of today's major generative AI systems are built using deep learning. But the easiest distinction for beginners is the type of output being produced. A fraud detection system might output fraud probability 92%. An image classifier might output dog. A generative AI system might create a new email, a new image, a new program, a summary, or a new explanation. That doesn't mean generative models aren't making predictions internally. They are. The difference is what those predictions are being used to produce. Generative models learn patterns in data and use those patterns to generate new outputs. So remember, classification commonly produces categories. Prediction can produce labels, scores, values, or probabilities. Generative AI produces new content, and modern AI applications can combine all of these capabilities. How does generative AI actually create something new? The answer depends on the type of model. Let's start with large language models. An LLM processes your prompt and predicts a likely next token. A token might be a word, part of a word, punctuation, or another unit of text. Then it uses the growing context to predict another token, then another. Repeated many times, those token predictions produce paragraphs, code, summaries, and conversations. But don't assume every generative AI model works exactly like an LLM. Modern image generation systems may use techniques such as diffusion, where the system learns how to transform noise into structured images. Different architecture, same broad goal. Learn patterns from data and use those patterns to generate new content. So when someone asks, how does generative AI generate? The accurate answer is, it depends on the model architecture. For LLMs, next token prediction is one of the most important concepts to understand. Now let's zoom in on large language models. A developer pastes a complicated infrastructure error into an AI assistant. A storage adapter dropped. vCenter raised an alarm. And a virtual machine suddenly went read-only. The model can analyze the text, connect information across the prompt, explain likely relationships, and generate a response. That's an example of an LLM. Large language models are neural language models trained on enormous amounts of text and token data. Most modern LLMs use the transformer architecture, which is especially effective at modeling relationships across sequences. During generation, the model uses the context it has received to predict tokens and construct a response. That's why LLMs can perform tasks such as answering questions, summarizing documents, generating code, extracting information, classifying text, and participating in multi-turn conversations. So remember, generative AI is the broader capability. LLMs are a major family of models, focused primarily on language. You don't need to memorize every large language model on the market. Instead, understand 5 concepts. 1. LLMs are neural language models trained on enormous amounts of text and token data. 2. Most modern LLMs are based on transformer architectures. Transformers are especially effective at modeling relationships across sequences and context. 3. During text generation, an LLM predicts tokens. It predicts a likely next token, adds that result to the context, and continues the process to construct a response. 4. Scale has played an important role in modern LLM capability. Increasing model capacity, training data, compute, and improving training techniques can produce stronger capabilities, but simply making a model larger doesn't guarantee that it's better at every task. And 5. LLMs are general-purpose language models. The same underlying model can potentially summarize text, answer questions, generate code, extract information, classify content, and participate in conversations. So don't memorize model names. Remember the mental skeleton. Language model. Transformer-based in most modern systems. Token generation. Scale matters, but isn't everything. And one model can support many different language tasks. One reason modern generative AI became so powerful is scale. Traditional machine learning can sometimes solve useful problems with relatively modest, carefully prepared data sets. Deep learning often benefits from much larger data sets and more compute, especially for complex inputs such as images, audio, and language. And today's frontier foundation models can be trained using enormous amounts of data and computing infrastructure. But don't turn that trend into a definition. A machine learning model isn't defined by being small. A deep learning model isn't defined by always having more data. And a generative AI system isn't automatically larger than every predictive model. Scale is an important characteristic of many modern AI systems. It isn't what defines the categories. What defines them is the underlying approach and what the system is designed to do. Quick recall check. One system reads an email and returns spam. Another system receives a product description and writes a completely new marketing announcement. Which task is generative? The second task is clearly generative because the requested output is new content. The first task is classification. But here's an important distinction that will put you ahead of many beginners. The type of model and the task you're asking it to perform aren't necessarily the same thing. A traditional machine learning classifier could classify the email as spam, but a generative AI model such as an LLM could also be instructed to classify that same email. The underlying model may be generative even when you're using it to perform a classification task. That's why you shouldn't identify the technology based only on one output. Ask two separate questions. What type of model or system am I using? And what task am I asking it to perform? An LLM can generate an email, summarize a document, extract a name, classify a support ticket, write code, or answer a question. Same underlying model family, different tasks. That's a much more accurate way to think about modern AI. Here's an important distinction that has changed as AI applications have become more advanced. A traditional search engine retrieves information from an index and points you toward existing content. A base language model works differently. It generates a response from patterns learned during training, plus the context you provide. That means the model can produce an answer that sounds convincing even when the details are wrong. But modern AI applications can combine generation and retrieval. An LLM can be connected to web search, company documents, databases, APIs, or other tools. A common architecture called Retrieval Augmented Generation, or RAG, retrieves relevant information and gives that information to the model as context before it answers. So don't say, generative AI never looks anything up. Say, the model generates. The surrounding AI application may retrieve information, and tools can give the model access to external systems. That's a much better mental model for modern AI. Here's a 5-minute exercise. Open any free chat tool and give it a 2-part prompt. Explain the difference between machine learning and deep learning to a 12-year-old. Then ask for one IT example of each. The real value is checking its answer against what you learned here. If it says deep learning is just more data, you'll catch what it missed, and that'll prove you actually understand it. Treat this as a decision guide, not a rigid ladder. First ask, can precise rules solve the problem reliably? If yes, you may not need machine learning at all. If the system needs to learn patterns from historical data to classify, score, or predict outcomes, machine learning may be appropriate. If the problem involves complex data such as images, speech, or natural language, deep learning may become especially useful. And if the goal includes generating new text, images, code, audio, or other content, generative AI may be part of the solution. But modern systems often combine these approaches. An application might use machine learning for anomaly detection, deep learning for image recognition, and an LLM to explain the results. So don't ask, which technology is best? Ask, what problem am I solving, and which approach gives me the best combination of accuracy, cost, speed, explainability, and maintainability? That's the engineering decision. Here's how an interviewer hears the difference. The beginner says, AI, machine learning, deep learning, and generative AI are basically the same thing. The stronger candidate says, AI is the broad field of building systems that perform tasks associated with intelligence. Machine learning is an approach within AI that learns patterns from data. Deep learning is a type of machine learning based on multi-layer neural networks that can learn complex representations. Generative AI focuses on producing new content, and most modern generative AI systems are powered by deep learning. Then if they ask, where do LLMs fit? You answer, large language models are a major family of modern generative AI models focused primarily on language. 5 sentences. No buzzword soup. No pretending every concept is identical. And no forcing the entire field into one oversimplified diagram. That's the answer that shows you understand the relationships. Here's what these technologies can look like inside a real IT operation. Your monitoring platform receives thousands of infrastructure metrics. A machine learning anomaly detector notices that latency has moved far outside its normal pattern. That alert starts an incident workflow. Now an AI assistant retrieves the relevant logs, monitoring data, previous incidents, and troubleshooting runbooks. The large language model analyzes that supplied context and drafts a plain English incident summary, likely causes, recommended troubleshooting steps, and a handoff for the on-call engineer. Notice what's happening. Machine learning detected the abnormal pattern. A generative AI application helped interpret and communicate the evidence, and retrieval gave the LLM information specific to your environment. You don't need to force machine learning, deep learning, and GenAI into separate steps just to prove they're different. Real systems combine the technologies that actually help solve the problem. That's the architecture mindset employers care about. 3 mistakes can make it obvious that someone memorized AI terminology without understanding it. Mistake 1. Treating an LLM like a database or search engine. A base LLM generates responses from learned patterns and supplied context. Modern AI applications can connect it to search, RAG, databases, and tools, but generation and retrieval are still different operations. Mistake 2. Assuming every AI system learns from data. It doesn't. Rule-based expert systems are still part of AI. Machine learning specifically refers to approaches that learn patterns from data. And third, treating deep learning as simply machine learning with more data. The defining idea is the use of multi-layer neural networks that learn representations from data. More data and compute are often involved, but they're not the definition. Fix those 3 mistakes, and you'll be much better prepared for the follow-up questions. Here's a bad interview diagram. 4 completely separate circles. AI, machine learning, deep learning, generative AI. What's wrong with it? Machine learning and deep learning aren't independent competitors. Machine learning sits within AI. Deep learning is a type of machine learning. Now look at generative AI. Most of today's major generative AI systems are built using deep learning, so there's a strong overlap. But generative AI tells you something different. The system is designed to generate new content. That's why the better interview explanation isn't simply 4 circles. Explain the relationships, then explain what each term tells you about the technology. If you can do that without hiding behind a diagram, you actually understand it. Let's lock the entire video into 3 takeaways. 1. Know the hierarchy. Artificial intelligence is the broad field. Machine learning is a major approach within AI. Deep learning is a type of machine learning based on multi-layer neural networks. Generative AI focuses on generating new content, and most modern Gen AI systems are powered by deep learning. Large language models are one major family of modern generative AI models. 2. Match the technology to the problem. Rules may be enough for predictable logic. Machine learning can learn patterns for classification and prediction. Deep learning becomes especially useful for complex data, such as images, audio, and language. Generative AI becomes useful when the system needs to create or transform content, and real systems can combine them. 3. Understand generation versus retrieval. A language model generates, search retrieves. RAG combines retrieval with generation. And tools can let an AI application interact with APIs, databases, and other systems. If you can explain those 3 ideas clearly, you've moved beyond memorizing AI buzzwords. You understand how the major pieces actually fit together. If you want the step-by-step path from IT beginner to pro, including where AI and machine learning skills fit into cloud and support roles, download the free IT Career Roadmap from the description. It's the same resource I'd hand a new teammate on day 1. Go grab it. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.